Hello everyone, welcome back to my channel. Today we're going to go over this problem of fluid mechanics. So this is a problem and we're going to read the problem. An open water manometer is used to measure the gas pressure in a tank. The tank is half filled with 50,000 kilograms of a liquid chemical that is not miscible in water. The manometer tube is located just below the free surface and is filled with liquid chemical. What is the gas pressure in the tank relative to the atmospheric pressure? The answer is 1,410 pascals, which is gauge pressure, which means it is relative to the atmospheric pressure as they said. So what is a manometer? We first have to understand how a manometer works. So a manometer is a device that measures fluid or gas pressure, often in HVAC laboratory and medical fields to detect differential pressure or system airflow. Common types include the U-tube manometer for basic differential pressure measurements, the inclined manometer for improved accuracy with low pressure changes, and modern digital manometers for versatile high-resolution readings of feature like data logging, and the choice depends on application accuracy needs, portability requirements, and whether a visual or digital reading is preferable. So a manometer has like a U-shaped, it has two different sections of tubes, and basically inclined manometer is more accurate because of the incline. An incline manometer looks like this. Let's see if the image can click in. Yes. So this is what an incline manometer looks like. Um, Basically, it's more accurate because the incline allows for it to be more sensitive to changes in height versus a simple U-shaped manometer. So a manometer works by using the principle that pressure causes a liquid to rise or fall in a U-shaped tube. By connecting one end of the tube to a system whose pressure is being measured and leaving the other open to the atmosphere or another reference pressure, the difference in the height of the liquid into two arms directly indicates the pressure being measured or the difference between the two pressures. This height difference is a measure of hydrostatic pressure, with greater height meaning greater pressure. Um, so as you can see, here is a clearer example of how manometer works. We have case one, where we have only atmospheric pressure on both ends, so no pressure difference, and case two, where we have a pressure difference. So, and case three, where we have another type of pressure difference, where the atmospheric pressure is greater than the pressure of the other end, basically. And another case where atmospheric pressure is less than the pressure on the other end. So let's move back to our problem. Um, let's see. So in a manometer, um, it's about balancing the pressure, and the height corresponds to the amount of pressure. So for instance, we can call this point over here point 1, this point over here point 2, and this point over here point 3. And point 1, there's going to be atmospheric pressure and also the pressure at here, which is just atmospheric pressure because of continuity. The pressure at the surface of the level of the water is going to be equal to the atmospheric pressure. That's a continuity, um, that's from continuity. And we are going to call this height over here height 1, and this height over here height 2. And height 2 is the 50 millimeters, height 1 is the 400 millimeters, and height 3 is going to be the 225 millimeters. So similarly, because we are in a manometer, the pressure at this point over here must be equal to the pressure at point 2 since they're on the same height level. And also the pressure at 3 is at the pressure at the liquid gas interface. It's the pressure at the surface of the liquid. And that is going to be due to the pressure due to the gas. Um, and this is what we want to find. We want to find the pressure at point 3. And we can do this by analyzing the manometer. So pressure at 3 equals, this is what we want to find. And we can find this expression by first finding the pressure at point 2. Because the pressure at point 2 can be related to the pressure at point 3. So for the pressure at point 2, the pressure at point 2 is equal to the pressure at this point over here since they're on the same level. So we can calculate simply the pressure at this point over here. And the pressure at that point over here is going to be equal to the atmospheric pressure plus the density of water times gravity and times the height difference, which is H1 minus H2, basically this column of water. H1 minus H2. And if we think about this, basically, the density of water times gravity will give us the mass. Wait, hold on. The density of water times gravity is going to be equal to the density times gravity is going to be equal to the mass over volume times gravity and mass times volume, mass over volume. So mass yes, so basically density is equal to mass, which we can represent as kg over volume, which is meters cubed, and gravity is equal to meters squared. Oh, wait, meter over second squared. So as you see over here, the meters cancel out, so we have meters squared on the bottom then. And then this value is going to be in meters. So we actually have meters over meters squared, which will give us meters. So we have kilogram meter over seconds. Kilogram meter over seconds. Let me see if that is correct. Yeah, so this will give us kilogram meter uh over second squared, I believe. No, sorry. Kilogram kilogram over meter second squared, and this is the same unit as force divided by area, which is force is in newtons, which is kilogram meter over second squared, and then area is meter squared, so we have kilogram over meter second squared. So here we also have kilogram over meter second squared, which is the unit for pressure. So by unit analysis, this is the correct format. And basically, this equation comes from the fact that the pressure at this point must be able to support the pressure of the column of water acting down at that point. And the pressure of that column of water acting down at that point is equal to the weight of the water, um, and the weight of the water is acting on a cross section, a circular cross section, which is going to create a pressure at that point. And the pressure at that point is going to be equal to um, that one because it is in static equilibrium, and by force balance, it has to be true. Um, yes, which is why we have this column of water times the density of that water times the gravity of that water. And because the volume is directly proportional to the height of the water. So that is going to be the pressure at the second point. Um, what about the pressure at 3? So the pressure at 3 is going to be the pressure at A minus the hydrostatic pressure due to this column of liquid chemical. And it is minus because the pressure at point 3 is obviously going to be less than the pressure at 2, since it is at a higher height in the manometer than point 2. So that's why we subtract when we are going up the manometer and why we add when we're going down the manometer, because the pressure increases the lower in the manometer um, a point is. Um, yeah, so basically the pressure at 3 is going to be equal to the pressure at 2 minus the hydrostatic pressure of the chemical, which is the density of the chemical multiplied by gravity multiplied by H3, which we define to be the 225 millimeter. And this is the same kind of for the same kind of reason as the reason we described previously. That's why we use the density of the chemical, because this column is going to have some weight associated with it, and that weight is going to create a pressure at point 2. Um, and and also a pressure at point 3, because the gas also is pushing down on this liquid. But because of continuity, the pressure at point 3 must be equal to the pressure exerted by the gas, which must be equal to the pressure at the surface of the liquid. Mm. And yes, if we rearrange this equation, we can also see that P3 plus the rho density of the chemical multiplied by gravity multiplied by H3 is equal to P2. And this makes sense because it's just that instead of atmospheric pressure, the atmospheric pressure in quotation marks over here is the pressure of the gas. Over here we had atmospheric pressure plus the height of the column multiplied by the density of water multiplied by gravity. But over here we have the pressure at point 3, which is the pressure of the gas, um, plus the density of the chemical times gravity times the height of the column of the liquid chemical. So it is the same kind of analogy and way of thinking, except over here we have the pressure from gas instead of the pressure from mm, the atmospheric gases. It is a different sort of gas. And yes, so now we have to calculate the density of the chemical. And how we do that is we have to first calculate the volume of the liquid chemical. because density is equal to mass over volume. So let's go ahead and calculate the volume of the chemical. So the volume of the chemical is going to be equal to, if we can divide this into three sections, we can see that these two hemispheres actually form a complete sphere. So instead of calculating it two separate times, we only need to use the volume for a sphere in our calculation. And that volume is going to be equal to 4/3 pi r cubed. And r over here is going to be the 2 meters. So it's going to be first equal to 4/3 pi 2 meter cubed. And then the rest in the middle, we have a cylinder. And the volume of a cylinder is going to be the area of the circle times the height. And this part is going to be equal to 10 minus 2 times 2 meter, which is 10 minus 4, which is equal to 6. And the area of this face is going to be pi 2 meter squared, pi r squared. So it's going to be equal to 4 pi. So the volume of the cylinder is thus going to be equal to 4 pi times 6, which is equal to 24 pi, I believe. However, we have to remember to halve this because um because the volume of the liquid in the tank is only filled up to 1/2 the height. So we divide this by 2, and calculating that we have first of all the volume of the whole tank is equal to 108 about, and the volume of the liquid chemical is thus equal to 54.45 meters cubed. Now we have the volume of the liquid chemical. We have to find the density of the liquid chemical. And the density is going to be the mass of the chemical divided by the volume of the chemical, which is equal to 50,000 kg over 54.45. And we get that this is equal to 918.2 kilogram per meters cubed. Now let's see if we have all the needed equations and information needed to calculate P3, or the gas pressure in the tank. It looks like we do. But first we have to express P3 in terms of all known quantities. P3 is thus equal to P2, which is plugging in P atmosphere, plus the density of water times gravity times the difference in heights, minus the density of the chemical times gravity times the height 3. So the atmospheric pressure is some quantity that we have to become familiar with, or we have to memorize, because the atmospheric pressure is equal to 101.3, I think, kilopascals. An alternative method is that we can just get everything in terms of gauge pressures here, which is relative to the atmospheric pressure, and express P3 as equal to the density of water times gravity times H1 minus H2 minus the density of the chemical times gravity times H3. Or you can calculate it this method and simply subtract the atmospheric pressure at the end in order to get what they asked us, which is gas pressure in the tank relative to the atmospheric pressure. I find that this method can be a little more confusing since we get it in terms of the atmospheric pressure more early. So I'm going to use the previous equation, which is this equation over here. So atmospheric pressure is equal to 101,300 pascals. And then the density of water is equal to 1,000 kilogram per meters cubed. And then gravity is 9.81 meter per second squared. And then H1, height 1 is 400 millimeter, which is 0.4 meters. Height 2 is 50 millimeter, which is 0.05 meters. And uh, the density of the chemical is 918.2 kilogram per meters cubed. Gravity is 9.81 meter per second squared. Height 3 is equal to 225 millimeters, which is 0.225 meters. So calculating all this, we have that the pressure at 3, and then we add an absolute in order to not confuse ourselves. And it is absolute because we accounted for the P atmosphere here. If the P atmosphere were not here, this will not be absolute, but gauge, which is what we wanted to find, the pressure relative to the atmospheric pressure. But here we're going to get everything in terms of absolute pressure first, just to not confuse ourselves. Calculating this, we have that P3 is equal to 102,706.8 pascals. And this is absolute pressure, but in terms of gauge, it will be equal to 102,706.8 pascals minus the atmospheric pressure, which is 101,300 pascals. And this will give us 1,406.8 pascals, which is rounded to 1,410 pascals, which is what we wanted because P3 is equal to the gas pressure in the tank relative to the atmosphere over here because of continuity at the liquid chemical and gas interface. So I hope that this problem helped you guys think through these sort of problems, and I'm going to post these slides afterwards. And don't hesitate to reach out to me with any further questions. See you in the next video.